It's one of the most explosive displays of power in the entire natural world. A 500-pound predator launching itself with breathtaking speed. We can all see the tiger's raw strength, but the real secret to its power isn't just the size of its muscles. It's hidden deep inside, at the cellular level. You've probably heard the claim that tiger muscles are 70% fast twitch. But what does that number actually mean? Research shows that the powerful locomotor muscles of large felines are dominated by fast twitch, or type 2, fibers, with some studies measuring a composition of 50% to over 70% in key muscle groups. This specialized makeup is what makes a tiger a perfect ambush predator. So, how does it turn this big cat into nature's ultimate biological spring? Before we can get the tiger, we have to get ourselves. Every animal with a spine, from a tiny mouse to a blue whale, has skeletal muscles built from two main ingredients: slow twitch and fast twitch fibers. Think of it like the meat on a chicken. You've got the dark meat, the legs, and the white meat, the breast. That's not just a dinner preference, it's a biological reality. The dark meat is dark because it's flush with a protein called myoglobin and packed with tiny cellular power plants called mitochondria. These fibers are built for endurance. They use oxygen for a steady, consistent supply of energy, which makes them incredibly resistant to fatigue. These are your type I, or slow twitch, muscle fibers, the marathon runners of the body, powering sustained activities like walking and standing. Then you have the white meat. It's lighter because it has way less myoglobin and fewer mitochondria. These fibers don't bother with the slow burn of oxygen. Instead, they run on stored energy, using anaerobic pathways to unleash massive force almost instantly. These are your type 2, or fast twitch, muscle fibers. They're the sprinters, built for explosive movements like jumping and pouncing. The catch? That energy burns out incredibly fast, and they get tired quickly. So, you've got two settings: the slow and steady endurance machine and the fast and furious force generator. The specific blend of these fibers dictates an animal's athletic talent and its entire survival strategy. So, where do we humans land on this spectrum? If you took a muscle sample from an average person, you'd find a fairly balanced mix, often hovering around a 50/50 split, or a slight majority of slow twitch fibers in major leg muscles. In essence, our biology doesn't lean dramatically one way or the other. This muscle fiber composition is a ghost of our evolutionary past. As our early ancestors moved from the trees to the ground, our muscles adapted. We traded some of the explosive strength of our primate cousins for something else: incredible endurance. This slow twitch foundation allowed our ancestors to become persistence hunters, capable of tracking prey for miles and miles, literally running them to exhaustion. Our bodies are designed to be metabolically efficient and cover long distances without gassing out. Of course, there are outliers. The leg muscles of an elite marathon runner might be composed of 85% slow twitch fibers, making them the ultimate endurance machines. On the flip side, an Olympic sprinter could have leg muscles with up to 75% fast twitch fibers, giving them that genetic edge for explosive speed. But for the most part, humanity is a species defined more by stamina than by sheer power. This becomes crystal clear when we look at one of our closest relatives. For decades, we've heard stories about the super strength of chimpanzees. While some tales are exaggerated, the truth is rooted in their muscle biology. Unlike humans, a chimp's muscles are heavily biased toward power, with some studies indicating a composition of roughly 2/3 fast twitch fibers. They are quite literally built differently from us. This difference in fiber type means that chimpanzee muscle can generate significantly more power and force than human muscle of the same size. Their bodies are geared for the explosive, dynamic strength needed to climb and fight. This fast twitch dominance highlights a crucial fork in the evolutionary road. The shift in early hominins toward more slow twitch fibers was a trade-off. We sacrificed some of that raw, explosive power for a more energy-efficient body, one that allowed our ancestors to spread across the globe. This comparison gives us a vital piece of the puzzle. If a chimp, with its fast twitch advantage, is that much more powerful than a human, what happens when you push that ratio even further? What happens when you engineer a predator that is overwhelmingly fast twitch? You get a tiger. This is where it all clicks into place. A tiger's body is a masterclass in predatory evolution, and its muscle fibers are the secret sauce. While the exact percentage varies, studies on large felids like lions and caracals show a massive majority of type 2, or fast twitch, fibers, often ranging from 55% to nearly 70% in their powerful hind limb muscles. It's a complete specialization. A tiger's entire hunting strategy is built around the ambush. It relies on stealth, getting impossibly close to its prey before unleashing a sudden burst of overwhelming violence. Those fast twitch fibers are what make it possible. They act like high-tension springs, ready to release an insane amount of energy in a split second. When a tiger attacks, its muscles heavily rely on anaerobic pathways burning through stored energy to generate power with blinding speed. This allows a tiger to lunge several meters in a single bound and deliver paw swipes with enough force to shatter bone. Its hind legs, which are longer than its front legs, are like massive pistons that provide the propulsive force for these devastating attacks. This is the same principle at work in lions, which have a similarly high proportion of fast twitch fibers and excel as ambush predators. In fact, one study found that the individual muscle fibers of a lion could produce nearly 3 times more power than a human's. A tiger's power output would be in the same terrifying category. But this incredible power has a huge trade-off: stamina. The fuel for these explosive movements burns out fast. A tiger can't maintain its top speed for more than a few hundred feet. It either succeeds in its initial ambush, or it risks total exhaustion. This is the fundamental compromise of its biology, sacrificing endurance for a level of explosive power that's almost unmatched. A tiger doesn't exist in a bubble. Its evolution has been a constant battle with the animals it hunts, an arms race written in their very muscle fibers. You might think prey animals would be built like marathon runners, all slow twitch to outlast an attack. But nature is a bit more clever than that. Take the antelope, a common meal for big cats. You'd expect its muscles to be the polar opposite of a tiger's. But studies have found something fascinating. Antelope muscle composition is remarkably similar to that of big cats, with a high percentage of fast twitch fibers. So, how do they escape? Evolution gave them a special trick. While their muscles are built for speed, many prey species have fast twitch fibers that are also highly oxidative, meaning they have better fatigue resistance. They get the explosive getaway speed of a sprinter but can sustain a high velocity for much longer than their predators can. It's a biological checkmate. The predator evolves explosive power for the attack, and the prey evolves explosive power with just enough endurance to escape it. So, what does it really mean for a tiger to be loaded with fast twitch muscle? It means a tiger is the ultimate specialist. It has sacrificed the all-around utility of an endurance animal to become a perfectly honed killing machine, optimized for one thing and one thing only: the ambush. Its muscular system is a monument to this strategy. The powerful, fast-twitch dominant muscles in its limbs provide the explosive force needed to take down prey several times its own size. Its muscular forelimbs and flexible shoulders are designed for grappling and controlling struggling animals. Its entire skeleton is built to maximize the power generated by this specialized system. When you compare this to our own evolutionary path, the contrast is stark. Our ancestors developed a more balanced muscle profile to become persistence hunters. We traded brute force for stamina. The tiger went the other way. It perfected the art of the sudden, overwhelming assault. It doesn't need to run a marathon. It just needs to win the first 10 seconds of the fight, and its entire biology, right down to the cellular level, is designed to make sure it does. A tiger's low high-speed stamina isn't an evolutionary flaw. It's the defining feature of its success as an apex predator. This incredible specialization is what makes the tiger one of the most formidable hunters on the planet. If you found this look at animal biology fascinating, make sure to subscribe and hit that notification bell for more deep dives into how nature's most amazing animals work. Let us know in the comments which animal's secret biology you'd like us to explore next. From a single muscle cell to the explosive pounce of a 500-pound predator, the tiger's strength is a story of evolutionary focus. That fast-twitch dominance isn't just a number, it's the biological signature of an ambush artist. It represents a trade-off, where millions of years of evolution sacrificed marathon running endurance for the split-second, fight-ending power needed to rule its domain. Understanding this incredible biological design makes it all the more critical to protect these magnificent animals. Their strength defines their place in the natural world, but their survival depends entirely on our commitment to preserving the wild spaces they call home.